to make the process live on YouTube. Give me about 30 seconds to complete that. That link later I will share so that you can refer to it anytime you want. And also on the same channel, there are many other videos on by other experts that you can refer to. As soon as it's live, I'll just mute it so we don't get the echo. Right, it's muted, so there you go. Now we'll have a link for you to look at. Right, so we go again, and this time I think we'll take it further. So advantages of TIG, as we were discussing, the best welding processes, cleanest looking, very good looking beads, aesthetically very pleasing, no spatters, so no post-process cleaning. All position welding is possible to automate. Disadvantages were slow, poor arc stiffness, low depth of penetration, larger HZ. Because you have a slower filling up of the weld pool, the heat affected zone is larger. Skill level of the welder required is high, especially if you're looking at aluminum welding or even at good stainless steel welding for extra quality welds. Stubborn losses are higher, therefore deemed expensive. What can we do to increase the productivity there? So let's look at the manual process today. It requires filler material to be fed manually. Different sizes of filler wires are used for different passes. So if you're doing root, filling, and capping, you would either use a 1.6, a 2.4, or a 3.2 mm filler wire. Frequent start-stop. So each time there is an end of wire, the operator has to stop the welding, pick up another filler wire, and restart the welding from there. This leads to overlaps on the start and stop. This is where the majority of your lack of fusion or lack of penetration is reflected. Post-process of grinding at all overlaps is required. Chances of LOF and LOP, lack of fusion, lack of penetration at overlaps is high. There are high level of stubborn losses, 4 inches for every 1 meter cut length, close to about 9 to 10%. And they normally need a helper to replace wire, change in currents, etc. This all makes the TIG process slightly more challenging or expensive. So we have something called a cold wire feeder, which can make the TIG welding process as good as a MIG welding process. That means the wire is fed automatically. If you can look here, this is a wire feeder with the torch with the feeding arrangement on the pin. So the idea is that the wire is fed automatically through the pen into the pool. This increases the welding speed because now the welder does not have to stop every time the filler wire is finishing. It reduces the stubborn losses, so about 10% material can be saved. It can simulate pulsing, so the welder has a habit of putting the wire in and out of the pool. The same thing can be simulated here. Allows for the wire on delay. So when you, if you're looking at the arcing, when you start the arc starts with an upslope. So it will start at a lower current and go on to the full current. And this helps get the molten pool stable. So as soon as the molten pool is stable, you want to feed in the wire. So you can add in a wire on delay, which allows you to start the wire feeding only after the pool has been formulated. You can retract the wire once the welding is over. So if it retracts, it doesn't stick into the pool, thereby giving you a very clean finish. It reduces the start-stop for the welder. The amount of fatigue that the welder goes through while each time he starts and stops is not there anymore. He can weld much longer at one go because he doesn't have to stop for the filler wire to be reloaded. It saves gas because each time you press start and stop, you are going through the cycle of post-flow and pre-flow again. So if you were to reduce your pre-flow, post-flow cycles by about 20, that would mean about 40 seconds of gas flow or 60 seconds or a minute or two of gas flow at about 8 to 10 liters per minute saved per meter of weld length. Now, there's another tool called a hot wire TIG. So hot wire feeder, what it does is it preheats the wire before it enters the molten pool. Now, by preheating the wire, it allows you to have a higher productivity rate because the wire is preheated, it melts faster, and the amount of current required to melt the wire reduces. There is another inherent advantage of this process. of the cold wire feeder is that you can increase the speed of the wire that you are using. So suppose you are using a 1.2 mm wire or a 1.6 mm wire, you need not have multiple wire sizes. You can use only this one wire size and increase the feed rate. By increasing the feed rate, you can increase the amount of weld deposit. So you don't need to have multiple stocks of wire sizes. You can use one wire size for all passes. Now here, if you are to preheat the wire before it enters the pool, the wire feeder would be feeding the wire from here. You have your normal TIG welding power source with the TIG torch and the workpiece. You could add a hot wire power source, which would connect to the same workpiece as a ground, and the negative would be connected to the wire tip where the wire is about to exit. So the length of the wire that exits the tip to the pool is the resistance or the extension that is created. The current of the hot wire passes through that and preheats the wire before it goes into the pool. This helps melt the wire faster, and in short, also helps you to do this process faster. It can have an increased deposition rate and reduces or lowers the heat input. So let's see the typical rates. If you look at the manual process where we are welding between 100 and 200 amps, a cold wire feeder can give you about 10 grams a minute, or say about 600 grams an hour deposition rate. But the same thing with a hot wire power source would jump up to about 20-25 grams a minute, or about 1.2 kgs an hour. That's a huge deposition change. Now depends on the joint configuration and other things, but this is a typical value. But when you look at moving into automation, you will see the welds at about 300 amps or above. The change in deposition rate is quite drastic. Now the cold wire feeder is available in 3 different settings. So you could either use the pen to feed in with the torch. So the operator holds the pen in one hand and the torch in the other. By not changing his technique of welding, he still holds the pen the same way he holds the filler wire. The adaptation to the technology is much faster. There are the international models which prefer, or welders prefer, the wire coming onto the same hand and keeping the other hand free. This is also available. You could mount the wire feeder on top of the torch itself, adjust the angle that you would like and the length of weld. Operator can stop the weld from the same button and use the welding. If it was in hot wire, we could attach the hot wire either here, like it shows here on this image, or it could have put on here on the pen by giving you the same flexibility. The process is very easily adaptable to any existing setup. So your operator could be using an existing machine or an old power source. The cold wire feeder can be interacted with the same one. And you can see the known change in the skill level of the welder. So the welder is holding the pen the same way he would hold his filler wire, and the torch the other way that he does normally. This helps the welder pick up the skill very fast and get into the welding regime. And if the welder wants to use with one hand on say butt joints or longer welds, that is also available with a special torch given here and as shown in the figure. It's easy to attach to any kind of welding equipment. So here you can see an old inverter setup. It can be connected to that. You could use any European machines. This could connect to that. You could use any old thyristor machines. It could connect to that. So there is no limitation of adapting this to any existing setup. You don't need to buy a new machine. You could just use the cold wire feeder with your existing setup. So least amount of change, maximum amount of gain can be had. If you look at the parameters just for comparison of a single 150 millimeter long butt joint, manual filler wire of 1.6 used to achieve a weld current at 138 amps, the welding was achieved at about 110 seconds. The same thing when used with a cold wire feeder, reducing the wire size from 1.6 to 1.2 to keep the same current. The feed rate was achieved at about 900 millimeters a minute. The welder could do the same welding in 96 seconds. Using hot wire and adding a small current of about 40 amps to the hot wire power source, the same hot welding could be reduced to 80 seconds. Increase in the productivity goes up to about 30%, and the material deposit can go up to about 25%. This can be discussed further on practice. This can go up as high as 40% and 50% in certain cases that we've observed. The challenges in adaptation that we face is single hand operations requires a change in welder skill set. Root welding with 1.2 mm filler wire is a problem. The operator is used to using a thicker filler, setting the root gap higher. Solution is we can give them a pen-based solution, no change in skill set, and a training program of between 1 to 3 days. We've seen wonders that the welders get retrained. By doing this, they can weld the root gaps same as 2.4 mm or more using the same 1.2 mm filler wire and getting an extra quality weld joint. There's a resistance in the welder, fear. They have a challenged mentality. They feel that if they use tools like this, maybe they have to work harder, longer, and they would have to work more. The solution to this is a certification or an upgradation program. The welder is qualified based on cold wire feeder. It's an upskill instead of a fear, and personal performance indicator for the welder, where he can say that I can weld the same weld at a higher skill than others, and I have a certificate to show that. Gives the welder a little bit of more motivation to do this. We have designed this certification course for the cold wire feeder, and we can execute it at your place also if there need be. Are there any questions with regards to this? If there are any, we can take it now. If you have a question, you could put it on the Q&A section. I can answer them now, or we can move ahead to the automated section. Mr. Kalyan Kumar, I will get somebody to connect with you and we can organize a demo at your shop for sure. Thank you very much. Anybody else, if they have any questions, or we can move ahead to the automated part. So if you're looking at automating TiG, there are 3 reasons for which you want automation. Either you want to increase your productivity, you want to have consistent quality, or you want a reduction in cost. There are 3 ends of a triangle. Usually you can get 2 out of 3, but you can aim for all 3. But then you should have a clear idea why you are going in for automation. Once you have answered this question, the focus on the other part of the solution will be on that. Can I explain about the feed rate control a little more? Sure. I'll just go back to those slides in a second. So if you look at the wire feeder on the image on the left, here there is a part which says you can have an increased speed control. So if you calculate the volume of the mass of the 1.2 mm wire and multiply that by the speed, you will get the volume of deposit. So while the welder is welding, if he wanted a heavier bead thickness, he could increase the wire's feed rate. You can set the feed rate right from 0.1, so that is about 10 millimeters a minute, to about 5 meters a minute. So that can be as high as in manual, you could feed in that kind of a rate if you wanted. This allows for the feed to control, that's the wire speed knob here. And the operator has the control in his fingers or his hand to control the wire feed rate. And as you increase, you have more deposits. So that's the basic thumb rule on it. Maybe I can go in a little more detail later to clear out the details on the actual calculation of the wire feed rate. Maybe we can take it at the end of this session. Here you can see if you can use 1.2 mm with 900 millimeters a minute, it gives you the same bead as you would get by a 1.6 millimeter wire used for the same size of fillet. When you increase and keep the same size fillet, you could increase the speed. You would have added the speed to 1100 millimeters a minute and reduced your time taken to weld to 80 seconds. Right? I will take it up a little more in detail at the end of the session. Now, the challenges that you have in automating a TIG is that your edge preparation may not be very good. So if you have grinding versus beveling, so if you're using beveling, you will have a machine bevel will give you a very clean, even surface, whereas a manual grinding will not give you even surface. It will have uneven surfaces. So you will have root face tolerances, fit up mismatches, ovalities, or uneven surfaces. If you're doing a say a shell of about 4 mm thick stainless steel or a 5 mm thick but 2 meters or a 3 meter diameter, the minute you roll the shell will try to self-fold downwards because of the ovality created or the load. You may use spiders to maintain the ID, or you may have ovalities. If you had a very thick shell, say about 30 or 50 millimeter thick shell, and rolled it, and then you would have grind the entire edge to prepare it, you will have uneven surfaces all across. So you will have an ovality in general, which is allowed to about 2 to 3%. So that itself means about 4 to 5 millimeters gap between the tungsten and the job as a variation. Odd shapes, rectangular tubes. So what happens if there is ovality or if there's a change in the arc gap between the tungsten and the job? As you increase the arc gap, the voltage increases, the current remains the same. As you decrease the arc gap, the voltage reduces and the current remains the same. Therefore, the overall power into the job, which is current into voltage, changes. So either you have lower heat input or very high heat input if the surface distance between the tungsten and the job changes due to ovality or mismatches. So that's a big challenge. If you have repetitive jobs, that means long seam, plate to plate, rolled shell, long seams or circular seams for shell to shell, flange to nozzle, pipe to flange, pipe to elbow, pipe to reducers. These are all easy to automate, repeatable jobs. You can do that. Odd shapes becomes a challenge. For example, you have multiple ports on a pipe, say for an hydraulic extension, for example, or if you have a tube header, for example, where you have 1,000 tubes coming out on one axis. There, the kind of welds you may require robotic applications or different kind of applications. So how do you do automation in TIG? You need basic systems, that means column booms, rotators, positioners. You need productivity enhancing tools, that is wire feeding units, weavers, oscillators, ABC slides, hot wire TIG power sources. You need to add these two together depending on the job you have to get an automated solution. We'll discuss the tools first, what the wire feeding units, weavers, oscillators, ABC slides mean. Once we understand that, we will go into some basic applications which I'll take you through to show you what kind of automation can be done and what kind of automations we can get through it. So if you look at automated wire feeding, you have motorized wire feeding. It can be single or twin wire. The wire motor itself can be geared stepper motor, servo pancake motor, or it can be a pancake motor or DC gear motor. It all depends on what kind of accuracy you want. We usually prefer either steppered motors, geared stepper motors, or servo motors to do this. It can give you a very wide range of controlled feeding, which could be right from 10 millimeters a minute to about 5 to 6 meters per minute. Wire feeders could be 2-roll or 4-roll, depending on the application again and the wire size. If you wanted better grip, no slippage, we would go for 4-roll, or our customized 2-roll feeders, which are machined, which give you a very good control on the wire feeding rates. You could use either a single wire or you could use a twin wire feeding arrangement, which is shown here. Twin wire is usually used depending on the deposition rate you want to achieve and the space availability, because the head becomes slightly larger. Right? A classic example of hot wire GTAW with twin wire used. This would be your weld pool, for example. You would have one wire which would be trailing, one wire which would be leading. The torch would be fixed. The job would move in this direction. The job setting is about 220 millimeters per minute. Leading outer edge of the pool. The lagging trailing wire is well within the pool. Wire feed rates are 2.4 meters per minute each. Wire diameter 1.2. Current is about 270 amps, 15 to 17 volts. Hot wire at about 25 amps each. Shielding gas was 12 to 16 LPM and tungsten of 3.2 mm was used. This gave us an output of about 2.52 kgs deposit per minute. So if you look at it, this is 2.52 kgs deposit per hour. Same with a single wire hot wire could be achieved at about 1.14 kgs per hour. And with only cold wire, we could achieve 1.2 kgs per hour. So for this particular job, 225 amps were used, 15 to 17 volts. but you can see the travel speed of the job moved from 150 to 180 to 220 millimeters per minute, giving you a productivity increase right from 20% to about 45%. The same thing if you were to do in manual TIG, your speeds would be somewhere at about 50 to 60 millimeters a minute. So you're going from 50, 60 to about 150 millimeters by going to auto TIG. And then by adding hot wire, you're going to 180 millimeters. And then by adding it to a twin wire with hot wire, you could go up to 220 millimeters per minute, right? And hot wire would increase 20 to 25 amps only. Now, what are weavers or oscillators? I believe you would have seen most of these in automation. It's used to cover a larger area. So these are linear weavers. Either they could be used in 2G or 1G position. You can see a linear movement top to bottom. It allows you to do fill up and capping runs much better. Also for fusion of root, we will see that. But it simulates the hand movement of the welder that you could see, right? And there are two critical parameters here. If you look at it, one is the speed at which it is moving up, down. So it's the frequency or weaving speed. Second is the weaving distance, what bead size you would like to cover. And third is the dwell time. Now that's very important. You look at it when it's moving up and down, it pauses at the end at both edges, bottom and top. Now that's called the dwell time. It's more in the narrow groove kind of an angular weaving. We call this oscillation. Here you can see it pause to fuse the edges. If you don't pause or don't use the dwell time, you may get LOF or lack of fusion on the sidewall. To avoid that, you need to have a dwell time which is settable. This allows you to have good enough fusion at both ends. Right? This is a good solution for narrow groove. And what you saw on the top was for linear welds, 1G and 2G. Then you have the most important feature I would call for automatic TIG welding, which is called AVC or automatic voltage corrector. What that does is it helps you regulate the welding voltage. So as we were discussing, maintain the arc gap between the tungsten and the job fixed. If we don't do that, if we simply move the torch over here, when it comes to this part here, the arc voltage would increase drastically and therefore create you burnouts here. And at this end, it would dash and the tungsten might get stuck or your voltage would be reduced heavily. But the AVC takes the feedback of this voltage and adjusts this motorized slide to follow or track the profile. By doing that, you are getting the right set of voltage at every level all throughout the movement. Automatically also helps you maintain constant weld penetration on uneven surfaces. It helps you compensate for electrode wear. Now imagine you're doing a cladding job or you're rotating the job continuously and there is an ovality. This would move the torch up and down and ensure it maintains the same arc gap, therefore giving you even penetration all across the length, right? And it also can allow you a fixed distance from where you can start welding. I'll show you that more in an example as a video in the next couple of slides. Now, when you take the cold wire feeder, you take the AVC slide and the weaving slide and put them together, you have got an automated TIG head. Now, this automatic TIG head can fit into any of the tools that are existing. So your existing column boom, rotator, or you could put it onto a new column boom or an A-frame to get your desired solution. Now here I have shown you one on an A-frame. It just explains to you this is your torch. This is the AVC slide vertically, the weaving slide horizontally, and then you have the cold wire feeder and the hot wire power source to do the needful. Considerations for automation: part size, repeatability, time motion study, single or multiple station. Now it's very important that when you go in for automation, you're going to incur a lot of cost in getting the fixturing and the automation right. So your automation should be active most of the time. So if you have to do a good time motion study before you get into automation, so that you know if your loading unloading time is very large, then you should have multiple stations so that your welding time and your other activity can be paralleled, and so your system is not idle. I'll take you through a couple of examples: panel boilers for tube-to-tube welding systems for straight tube welding lines, titanium tube-to-tube welding systems on a similar line. You have butt welders, which are used for spooling operations for pipe to flange, pipe to elbow, reducers, floats, logs, smaller parts to be welded, low thickness, pipe to flange welding, long seamers, column boom with auto TIG heads, and A-frame with auto TIG heads. Now, this is a typical tube to tube welding, straight tube welding line. So you have one tube coming in, another boiler tube coming in. You have a fixed root gap you want to set. Torch comes down, touch retracts, starts the welding, and then the rotation happens. You have the cold wire feeder which feeds in the wire. This axis acts as weaving, this axis acts as AVC to give you X-ray quality joints. Here you can see the tungsten approaching the job when you start the cycle. It will approach and retract before fixed gap of say 2 millimeters, 3 millimeters, and then it starts the arcing. Once the arcing has started, the tube rotates. You can see the weaving in place. So you have a root gap that you had preset. It is welding with that root gap. The wire is being fed into the pool, and the entire job is rotating. Now these are for boiler tubes. They are 100% X-ray quality joints. Now your helper who understands the arc and where it should focus can do the same job of an RT welder without much difficulty now. You can see clearly the wire fed into the pool. This is the downstroke when it stops welding, so there is no crater formation, and a very easy overlap can be given. Same thing when you look at a bigger solution for your pipe to flange or your spooling operations. This is the A-frame, rotators, chuck, rotates the job, head remains stationary. You could position it on weld 1 or bring it here and position it on weld 2 and weld any of the joints that you wanted. This is the kind of finish you get. Now these are certain spooling or butt welding solutions you can see. So you have these pipe to flange joints, huge joints. By manual operation, that would have taken a couple of shifts, which could be reduced to a couple of hours. So you have a lot of saving. Again, the same, you have a rotary axis, you have the auto TIG head with AVC, cold wire feeder, and weaving axis. You have the Alex power source for 100% duty cycle, a chiller, idlers for your longer jobs, chiller for the continuous operation. Like you can see, one operator is operating 2 machines here. And this is the kind of weld, bead finish you can expect from it on a cladding or a butt welding solution, right? No need for post-process cleaning, grinding, etc. Similarly, if you had smaller pipe to flange joints or a wall joint or a float joint, you could use these same axes. So you have here, we have tilted the job in 45 degrees so that the fillet joint comes in 1G. By doing this, you are reducing the error of 2 axes down to 1 axis, which is covered by the AVC. So you can have a very good joint. Even if there was a mismatch between the flange and the pipe, it would be covered very easily. And you would always have the right weld joint between the pipe and the flange. Some classic examples to show you how this is using the same processes what we do. Now here, I'd just like to emphasize, you can change the nozzle to even reach parts which are typically difficult to weld, because there is no access or approach available easily on automation. But by using the right tools, AVC, weaving, and cold wire feeder, you can get the same results no matter what. Right? Here we have, as we were discussing, what if the job takes longer to weld, less time to weld, but equivalent time to load unload. So you could have a twin station, one station to load unload, the other station to do the welding. Again, sorry. If you can see, the operator weld is loaded the job into a fixture. He will use 2 hands to give a signal that it's clear and he can start. So it's loaded the job. It will rotate onto the other axis where the welding will automatically start. Here the weld speeds were as high as 800 millimeters a minute. This gives the operator enough time to put another job into the fixture, check its position properly, and then reload the job for welding. Operator fatigue is minimal. The machine is always in use. The welding is always on. By paralleling this task, loading, unloading, and welding, we are able to achieve more throughput from the same machine. So whenever you have smaller parts or parts which can take longer, we can always look at multi-stations for loading, unloading. This is a typical plate-to-plate or a long seam weld where you can put the two plates or the rolled shell here. These are copper fingers which will clamp through, and then you can have the AVC axis on the top, weaving axis on the side, and the cold wire feeder to do the long seam welds. You could place a camera there to show you the weld joint as the long seam proceeds. This was about a 4-meter long joint. We did this solution for the rail car sidewalls, which was stainless steel 2202 and 4000 series for the metro and the trams. We have done this solution. Now, if you had a larger job, big vessels, pressure vessels, and the likes of that, this is used for aviation. This is a part of the Chandrayaan-2 solid fuel carrier. You can see this is a 3.2 meter shell. They've used spiders to make sure that the job is absolutely centered and not oval. The head here has AVC weaving and cold wire feeder mounted onto a column boom setup. The headstock, tailstock rotates the job. We have the hot wire power source and the cold wire and the normal TiG power source pulse TiG, which is controlled. The operator sits on the panel here on this floor, and he can do the welding from there. Again, the same 4 things give you the solution. Similarly, if you wanted to do pipe to pipe, you could have one headstock, multiple position welds can be handed onto an A-frame. It can move along the axis wherever you want it. Weld joint could be here, here, or there, and the head can move in that direction and do the welding. So these are few of the things you could do. Then there is different welding process for overlay. Weld overlays, when we talk about vertical cladding station, horizontal cladding stations, this is a vertical cladding station used for cladding of walls, pipes, flanges on the ID and on the face. You could have a horizontal station to do pipes, ID cladding. And these are the universal cladding stations which can flip around and become a vertical or a horizontal station independently. When you want to do overlay or you want to deposit a lot of material on a different material, so these are carbon steel elbows, for example, lined with Inconel or Monel or stainless steel, that's when you want to use these stations. Here you can see an elbow being cladded, a narrow pipe being cladded from ID. This is a 2-inch bore, about 400 millimeters depth being cladded. Here you have the T being cladded, and here you can see the bore and the outer surface being cladded. We use the same processes of cold wire feeder, hot wire TIG, and AVC as the basic principles to do the cladding. The column boom and the outer fixture changes for the same. Here we have done 6 meter and 12 meter long pipes, ID being cladded in single, twin, or quad heads. You can see here in action, the layer is absolutely equivalent all across. So very, very uniform weld. That's because of the AVC that we are able to control. So this is where we can do automation and TIG, and we can get much more quicker welds. I'll just take up, I think there are some 3 questions. PQR may not support from your side, available for auto twin. Yes, we can support for the PQR and WPS during installations. Cladding of pipes, small bay may required for us. Okay, sir, we have that up to 50 mm ID. Post weld cladding, you can get a ID of about 32 is what we can do up to. Mr. Jamin Raval is asking, distortion will be same after automation? Not really. Your distortion levels will go down. Ideally, because your speeds will be higher and your heat input will be less. So if you're using pulse TIG and auto setup, say for example, I'll show you a 6 meter long weld being welded well within 15 minutes, for example. And if you're able to do that, your heat input is very, very low and distortion level is also much lesser. We are facing issues of the distortion and bulging of sheets up to 3 mm. MS aluminum SS is there, a distortion in manual TIG. So you could reduce the distortion by using pulse TIG, by using a cold wire feeder. It will reduce your heat input, and also by increasing your welding speed. If you move into automation, it will be much faster. If you have any particular product in mind, Mr. Jamin, we could discuss it offline, or you could send an email to us and I'll take it from there. Any other questions on that? All right. So I hope we've pondered a little more into this. Please go ahead and do a time motion study before you decide to do automation. Evaluate your welding time versus your handling time, which takes more. If handling takes more, we should go in for a handling automation or a robot to do pick and place rather than to do this. If you want, we can have another session on cladding itself. You can share details and we can have a detailed session only on cladding. It's a very deep subject in itself. But I would like to focus now upon making TIG even faster. So we discussed about going from 55 millimeters per minute in manual to about 150 millimeters or 200 millimeters in auto TIG. What if I told you you could go much faster in TIG, faster than even S.W.A.T? So we are talking about something called S.W.A.T or SigmaWeld accelerated TIG. It's a welding process based on keyhole technique. We generate a keyhole. It's an automated process, extremely efficient TIG process, no edge preparation required, 100% of time saved, up to 10 millimeter thickness. You can weld with or without filler wire. It's a square butt welding, very low heat input and very low distortion. What do I mean by that? How does it work? We basically constrict the arc. So whatever you see, the arc on a normal TIG covers an arc length of about this much. This is the width. We are making that width smaller. By making the arc constricted, the arc is more focused on a smaller area, thereby giving deeper penetration. How deep or what does it do? So if you look at a normal DC TIG, consider 100 amps, peak current 130, base current 50, effective current of about 100 amps, and pulsing of about 50% in peak, 50% in base. If you were doing this pulse TIG welding, your arc voltage would be about 9.8 volts. Arc force on the job would be about 3.2 millinewton, which would give you a weld bead appearance of about 2.47 depth and width of about 7.61 millimeters. This would be your bead appearance. If we did the same parameters by using S.W.A.T, our arc force would go up by 3 times. It would be 9.2 millinewtons, keeping more or less same voltage, same current. By doing this, your depth of penetration would go up by about 20% and your width would shrink by about 10%. How does S.W.A.T or keyhole TIG work? Basically, you have 2 plates, square butt put together. The torch is water cooled and rather sometimes even chilled to give you a good cold tungsten. And then the arc is initiated. The constricted arc burns through or pushes its way through all the way through the metal, creates a keyhole, and then you move the torch fast enough to maintain the surface tension of the weld pool. And the gases that are generated are exited through the keyhole on the other end. This is a very, very fast and effective method to weld square butt, welding of stainless steel and other metals, alloy steel, titanium, alloy. Now here is a small video which shows you 8 mm square butt weld. As you can see, there is no edge preparation, 8 mm thick, about 500 millimeter length. On this side, you can see once the arc has started, you will see this kind of a keyhole on the other side. This is called the efflux plasma. A clean efflux plasma shows that there is a very clean penetration all throughout, and it is giving you equal weld joint all through the joint. Here you can see the speed at which the welding is happening. This is something about 400 millimeters a minute. No edge preparation, single pass for an 8 mm plate. So in under a minute, you could do the plate could be welded. If you see the bead, it's no undercuts, nothing. We could use a trailing shield to give you a much better appearance, but this is just to explain the concept to you. The long seam welding, circular seam welding, tube mills, it can be used for all of these. Tube mills typically have a practice of using TIG plus plasma, which could be reduced to a single TIG torch. No oscillations, no wire feeder were required to do that. Materials that we have tried so far: stainless steel up to 10 millimeters. We recently did a 12 millimeter thick plate also in a single pass with a very minor chamfer on the top. We could do duplex stainless steels. We could do titanium up to 12 millimeters thick. We recently tried even 14 millimeters in titanium, and we got very good control on the weld. Nickel alloys, stellite alloys, and carbon steel. Carbon steel is the last to use, but all the others were very successful in the attempts we made. Here is a small chart to show you the nickel alloy being welded at about speeds of 550 millimeters per minute, stainless steel about 2.72 millimeters at 800 millimeters a minute, 3.1 at 770 millimeters a minute, 8 millimeters at about 400 millimeters a minute, 5 mm thick plates at about 500 millimeters a minute. So if you're a food or a pharma equipment manufacturer with a wall thickness of between 5 to 8 mm, you make shells of about, say, 2.5 meter long length, you could complete that weld joint in under 10 minutes if you so wanted, which right now would take maybe 2 or 3 shifts, right? This is the kind of weld joint you see. This is a macro of one of the penetrations that we are showing you. This is, you can see no over welding, and on the root side, there is a very good thick bead appearance available. This is welded at about 8.5 millimeter thick, 12-inch dia pipes, welded up to 300 millimeters per minute, which typically on the tube mill were being welded at 175 millimeters a minute. The kind of bead you can see, now this was a smaller thickness, maybe 4 or 5 mm, welded at 530 millimeters a minute. This is the kind of bead penetration you can get on the inside, consistency of the bead throughout the pipe length. It passes all the flaring tests and other bend tests that you go through, no cracks over there. And the macro RTR is all good to go. We did long seam welds of about 8 mm thick, 304 mm 1 meter length. This is just to show you how the speed increases. Your normal TIG welding would consist root plus 3 passes in manual. Typical weld speed of about 55 millimeters per minute. Edge preparation 30 minutes. Welding time per meter would be about, you're looking at 55 millimeters per minute. So say 20 minutes for 1 pass, and you have about 4 passes. So about 72 to 80 minutes for welding 4 passes. Total weld time 102 minutes. Not counting the start-stop time you would have to take to cool the plate down. You could not weld it at one go. Otherwise, you will have a lot more distortion. If you consider the cooling time, this would be anywhere between 120 to 150 minutes to do this job. Same thing in automated TIG. If you were to do, you could complete in root plus 1 pass. So you could do root weld with fire feeding and then 1 capping run. Speeds of about 100 millimeters per minute. Your weld time would be 50 minutes to do the same 1 meter length. In S.W.A.T, you could do this with 300 millimeters per minute. No edge preparation. Welding time per meter would be about 3.33 minutes. Your overall finish time would be well within 5 minutes. You could finish the entire job. From 102 minutes to 5 minutes. You can imagine the speeds achieved. This is a live example of HEST alloy. It's a very sluggish material to weld. Welders' skill requirement is much higher. It is a much slower process in HEST alloy. This is a 6 meter long plate, 6 mm thick. To weld this in manual, you would need about 3 to 4 passes, and it takes close to about 2.5 shifts to weld. So about 2.5 days to weld this particular plate right in front of you. This is before welding. We use S.W.A.T to weld this plate, square butt, straight up, and this is the post-weld finish. So no distortion can be observed. And also, if you look at the weld bead finish on the other end, the penetration end is much thicker as they wanted. The entire weld was completed at a speed of 420 millimeters per minute. The 6 meter long weld was completed under 15 minutes. This is continuously under production at one of the largest fabricators in India. And you can see here the edge preparation, you can see it's square butt, no edge preparation required. And here on the same fixture, we are doing the welding. This is the actual speed of weld that you can observe. Also, in this case, we are not adding the filler wire in the first pass. So no filler wire, completely welding in one go, achieving the entire weld within 15 minutes is a big change in the output. These have been tested as per ASME section 9, the bend test, tensile test, root bend test, phase bend test, and they have passed all of those parameters. So we come to the end of our discussion or the presentation. As a summary, TIG can be made faster, moving from manual to semi-automatic using cold or hot wire feeders. You could increase your speeds from 30 to 50% is possible in manual. In automated TIG, you could move from 150 to 400 millimeters a minute. You can take the speeds up to there using hot wire and cold wire and AVC. If you went on to S.W.A.T, you could move your speeds upwards of about 100 times because you can weld at 400 millimeters a minute, single pass 700, 800 millimeters a minute. In certain tube mills for 2 mm and up to 1 mm thicknesses, we have taken the speeds to about 2 meters per minute, which is very high speeds for tube mills, but that's the kind of productivity enhancements you can get. So now we can have questions if any. I can take them up. This is my email address. If you have any other questions at a later date, you could also send it to me. I'll just go through the questions now. Mr. Shashi Shekhar Kumar is asking, is auto TIG good for higher thicknesses? Yes, Shashiji, you can have TIG for higher thicknesses as well. We are done up to about 150 millimeter thick vessels also in auto TIG. Mr. Pinakin Parik is asking, would you visit our place in Savli and advise for automation? Sure, we can do that. Pinakinji, I'll share your details with my team. Jay is in Baroda itself. He will visit you and take it forward. Which process has less heat input? TIG has less heat input. S.W.A.T is even lesser, if you consider. Which material was used in the video for keyhole? Jaiminji, this material was C276, which is Hesta alloy, and it's a nickel-based alloy. What current was used for automated welding versus manual welding? The currents we had kept same for comparison. So I'll show that table again one more time, just for your awareness. When we did the this is for automated auto GTAW with cold, with hot wire and with twin wire. Currents are always same. In twin wire, we have to increase current because the second wire also needs to be melted through. If you look at the other sample also that I shared for manual, we kept the current fixed to decide how much more increment you can get. Ideally, when you do an automated welding, your speed goes up, your current can also go up, but your overall heat input will always remain lower. So you can calculate that and work on it on that way. Any other question if there is? All right. Anilji, am I audible?
Yes, sir.
Yes, Anilji. So I think we have covered the process. If there is any comparison or if there is any other questions we can take up, or if somebody wants to ask, we can unmute and have a dialogue or a discussion, and then we can take it from there.
Okay, sir. As I shown in the screen, there are total 14 questions, and from which the last questions, which material was used in video of keyhole technique?
That I just shared, it was Hesta alloy.
Hello?
It is Hesta alloy, C276.
Okay.
It was Hesta alloy. I think we took all the questions that were mentioned. If there's anything, any other question coming up?
Okay. This question is already asked.
So this is 276 or Hesta alloy.
I think we all have the understood the very well the presentations, and apart from this few questions, there is no any questions coming. One more question that is from the email level. Okay, the mystery Ajay wants to see once again the GTAW parameter.
Ajay ji, do you want it for the automated process? This is for the automated process, and the other one is for the manual process. So this is in auto TiG. If you are doing currents of 225 amps, 15 to 17 volts, travel speed of the job was 150 millimeters a minute. Wire feed rate was 1900 millimeters per minute, which roughly calculates to about 1 kg per hour. And if you were to look at the same for manual and that, I will show this. This is the table. So here the cold wire feeder speeds were 900 millimeters per minute and up to 1100 millimeters per minute. Now this completely depends on your particular job. So if your job desires or requires more fill up, we can take this up as high as about 4 meters per minute. Not a problem. I hope that answers your question. Jaminji, we can use keyhole technique for 2 mm stainless steel, and we can also do WPS again for keyhole technique. We can set the WPS once and then get it qualified. Pinakinji, the HZ will be lower. It will not be higher due to high speed because the overall heat input is much lesser. So if you look at the current and the speed, and you calculate the heat input, heat input is very low comparatively. So the HZ is not very high. Is a very small HZ. In fact, we did some things for ISRO where we did cellite and cobalt material welds, where because of the reduction in HZ, they were able to also look at considerations for reducing the overall weld thickness as well, material thickness, which would mean that their payload can go up much more in the explorations. Any other question? Yeah. Mr. Muralidharan, I will share the presentation, and it is also the video has been recorded. It's on YouTube. I will share the link with you as well. So if you want, you can have a look through that, and I will share the presentation as well. Not a problem. All right. So, Anilji, if you would like to take it from here.
Yes, sir. Thank you. I'm thankful to you that giving us so much interactive session about the special kind of TIG welding processes, and hope in future also we can do the another kind of level of this kind of presentations. And this time we have the enough participation, and in the next time we targeted more to join with this such a innovative ideas and presentations. I am once again thanking to SigmaWeld and the IW Baroda branch. And sir, one questions from my side also. I just curious about this keyhole technique.
Sure.
So, in that keyhole technique, is there any kind of development of heat affected due to that heat affected zone? Is there any kind of microstructural changes we observed in particular aluminum or non-ferrous material?
We've not tried much with aluminium, honestly. We've tried more to do with the sluggish materials to begin with. So stainless steel works very beautifully. We have tried with nickel alloys, Inconel, Monel. We did something like 19 variants of nickel alloys. and we were able to achieve very good results in almost all of them. So nickel alloys, Inconel, Monel, titanium. Titanium again, it's very, very difficult to weld.
Yes,
And
yes, yes.
manual welding requires a lot of cleaning and precaution. And each time you handle it, there is a risk of getting embrittlement involved. By using SWAT and reducing it to single pass, it makes it very, very effective as a method, and it will bring down the cost drastically for the overall manufacturing. Because you can imagine single pass welding of about 6 or 8 mm or a 12 mm or a 14 mm plate in titanium would be very, very interesting for many people. So we are doing certain trials. We've already done for 6 mm and qualified for aerospace. We are doing for one of my clients right now, we are doing something like 14 mm thick plate trials. And initial trials are successful. Now we are going to do some on their site as well.
Okay, okay. So you were not tried on the aluminum?
Not yet. No, not for aluminum yet. There
Is
is,
there any?
we are planning to do that soon.
Okay, okay. Means, is there any difficulties you are just, or the challenges which still you are not getting in that?
The demand for aluminum honestly was not so high as yet to do this process. We were stainless steel and, as I said, more exotic materials where welding becomes a bigger challenge is where we were focusing initially. So therefore, we are not even focused much on carbon steel. So we assume it's a process which will be expensive. It will be more better to do it for exotic materials and materials like stainless steel, where the cost effectiveness would really come around and the benefit would be seen.
Okay. Okay. Thank you very much sir, for kind information. I hope all of you have enjoyed this session and get the more knowledge in the TIG welding processes. In future, as I said, then in future also we are going to do same kind of webinars with the further improvements in the technology or advanced technology. I hope you are just once again given opportunity with you, so we can join with you once again.
Sure.
So thank you all from my side, and I hope if you share your link to me also, then I will share that link to our colleagues and all that.
Sure, we'll do that. We'll do that. I'll definitely share it across. And thank you everybody for spending your hour and a half with us. And sorry for the initial confusion between 4 and 4:30. We'll take care of that next time. And I really appreciate you being here and spending time on this. Thanks a lot, IIW Baroda branch, for giving us this opportunity and allowing us to share the knowledge with everybody. All right. Should we call it a day there? My email address is available with everybody. In case you have a question, please feel free to send a mail out. My mail ID is nchinoy@edmail.com. Get it on the slide box. And email me at SigmaWeld. All right. Thank you, everybody, for your time. And any questions, I'm free to answer. Thank you, Jignesh bhai. Thank you.
Thank you, sir.
Okay, thank you.